Okay, good morning. Any general questions as we get started? Okay, so I've posted homework 1 on Moodle. We can talk about it if we get an opportunity today or in the next class, but you can go ahead and take a look at it and start working on it. Okay, so we are on lecture 5. And we stopped at the place where we derived the expressions for in the last class. So we got the expressions for the dx for each for the panel that we were looking at. This is a panel that faces aft, right? So this is a panel that faces up and aft. So upper surface, aft facing panel. And then I asked you to, so we were pondering about whether this is plus or minus, and then we decided that with all the sign conventions we were using for this particular orientation of the panel, it's plus, and likewise the dy will turn out to be negative. So one of the things you have to figure out is for various panel orientations, will you have plus or minus for each of the dx and dy? So just to sort of continue along those lines, probably one good way to do this is to derive the expressions So you have upper versus lower surface and forward versus aft facing panels. So you can think about this by constructing a simple geometry. And this is not an exercise just for what we are doing here. In general, in many kind of engineering situations, let's say you have to create a model and then go and program it and then use it for something important. It might be your master's, PhD work, or it might be something else you're trying to do in the industry. Don't just jump in and start writing code, and even worse, don't write the whole code and then start running it and saying, oh, it doesn't work. Think through it always. Anytime before you write some code, this is what I do. I take scratch paper and scribble some things and make some little very simplified geometry, and then think through the problem for that, and then you code it. That exercise is so much useful because it helps you think through the problem and identify some bottlenecks and problem areas before you put it in code form. So this example I'm talking about is a fictitious airfoil, but still it will help you decide on some things before you start writing down equations and deriving equations and construct code. So let's say you have an airfoil like this. Leading edge, trailing edge, and this is upper surface, lower surface. This has got just 4 panels. You can actually work this out by hand. So if you put this into your code, and your code is not working, let's say your code is not working and you want to figure out why, you could create an airfoil like this, work it out by hand, and then put the same thing in the code, and then go make the code write out or debug it so that you make it write out the individual forces for each panel. And then you can say, oh, the problem in my code is for a panel that's on the lower surface facing aft. For whatever reason, you put a plus instead of a minus or something like that. So to make this easy, you could keep a constant CP on all four sides, a different value of a constant CP, and make it positive. So you can make it a positive constant CP. Maybe it'll be CP1, so, and then you put another constant or the same constant, doesn't matter, just these are all debugging situations. And then another constant but positive CP, and then something else here. And this particular situation is so fictitious that this airfoil may not even be generating positive lift. That's not the point here. It's not like you're going to make this for an airplane and go fly it, right? The point is to do such a simple case that you can do it by hand and check the code. So the correct So just by inspection, you can say certain things, right? For example, if you take this panel, the top rear facing panel, what would be the direction of dx and dy for this assumed pressure distribution? Dx is negative, dy is negative. You know that is the answer. So your equation should give that, the equation that you derive. Likewise, you will have a certain dx, dy sign for this, and so that's one way to derive the equations. And this is not, like I said, this is not for just this homework or a programming exercise. It's just in general engineering, many situations it helps to do such things. So there is another wrinkle in this. The expressions you derive and the positive or negative will depend on how the coordinates are ordered. And different catalogs, different data sources will order the coordinates differently. So in some sources, if you have an airfoil like this, they will start at the leading edge and they will go upper surface XY coordinates from leading edge to trailing edge, and then lower surface leading edge to trailing edge. Some other coordinates, airfoil coordinates will start at the upper trailing edge and they'll go around XY coordinates all the way around and they'll come here. And this could be flipped too. There may be some cases where it's like this. So think about it. So in this case, if you take a panel like this, this is 1, this is 2, right? If you go along the ordering of the coordinates. Whereas here, the same panel, if it's ordered like this will be 1 and this will be 2. So your dx, dy, small dy are really x2 minus x1, y2 minus y1. So it will be different in these cases. So these are all things to keep in mind. So in the homework 1, so there are two parts to this. Part A is where you check your code answers, code results with solutions that I've provided. So I've given you 2 example files, and I've given you the solutions too for lift and drag and pitching moment and everything. So you can check that. And then part B is where you will so here I've given you a whole bunch of data files, and you will, so for example, one problem will be we take a given airfoil at a given Reynolds number, and I've given you files for pressure distribution, for angle of attack. I'm just rattling off the top of my head. I don't know the exact angles of attack, but let's say it will be angle of attack 0, 2, 4, 6, 8, 10. So for each one, you run it through your code and you'll get lift coefficient, drag coefficient, moment coefficient. You make plots and you discuss what those plots mean. So discussion is an important part of homework part B. Part A, you don't need to turn it in. But it's really essential you get part A working soon so that you will have time to do part B. And this is something you turn in. Part B you turn in by a due date on Moodle. So the discussion part, we'll actually be doing a lot of the discussion in class, not for the specific files that I'm giving you, but in general. We'll be talking quite a bit about how does pressure distribution vary with angle of attack, how does lift and drag and all that vary with angle of attack. What is the difference between one airfoil that has a high pitching moment and another airfoil that has a low pitching moment, and that kind of stuff. So basically discussion will be, the discussion you'll do for these files will sort of go in parallel with the course. So if you're just following what we're doing in class, that will help you write the discussion. So part of all this is you're going to be developing expressions for dx, dy, and other quantities. With these you will be writing a program. So these data files will have CP and CF distributions. We've talked about CP distributions. We haven't talked about CF, but we'll be talking about them very soon. And so developing the expressions, we've probably done at least 50% of the work already. So you just have to figure out all those pluses and minuses and just sort of bookkeeping to make sure your program will work correctly. Okay, so let's talk about how the data files will look. Okay, so in the data files, firstly, the panels will always be ordered the same way. So the panels will be ordered from upper surface trailing edge to lower surface trailing edge. So you will have panels starting with the trailing edge and then going like this. So these 2 points will coincide. The first point and the last point will coincide. Okay, so chord is always going to be 1. So the point about this ordering of coordinates is you can derive your equations for this system, and that's all we'll do in this homework. So you don't have to derive it for multiple systems. You know the ordering systems, only this one is going to be useful for us. Leading edge will be at 0, 0 and trailing edge at 1, 0. So this point is going to be 1, 0 and this point is going to be 0, 0. And there may or may not be a point at the geometric leading edge. That is the coordinate list may not include a 0, 0, 0, 0 point. So the listing may be such that the points skip 0, 0. It'll have one point on the upper surface and then next one will be on the lower surface. It just happens to skip 0, 0. Many actual coordinate files are like this. The points won't be equally spaced, but it really shouldn't matter for you the way we are writing this code. Okay, so let me draw a sketch for this. So if you have XY like this, I'm going to zoom into the leading edge. So let's say you have an airfoil that's leading edge like this. You may have points going like this, and then there won't be a point here, but maybe it will be like this. So okay, let me write one more bullet item, and then we'll sketch it. The points on upper surface and lower surface do not necessarily So let's say you have x coordinates like this, right? The points, you may have points on the upper surface not evenly spaced. So usually there will be a tight spacing near the leading edge and tight spacing at the trailing edge and sparse spacing in the middle, right? But the points on the upper and lower surface may be at different x locations. So you won't, lower surface point is here, it may not coincide with the upper surface x location. And really all of these are not problems at all, but it's maybe helpful for me to tell you this beforehand so that you write your program accordingly. Don't assume that x locations will be the same on the upper and lower surface and so on. Okay, we can talk more as we proceed. You'll have some questions, I'm sure, as we proceed, especially once you look at the files and start writing your program. The data is going to be, so let's talk about what the data will include. So you will have a column in the data called UE over VINF, which is essentially it's the same as V over V infinity, which is the velocity distribution on the surface of the airfoil. So we've already talked about V over V infinity. So if you know V over V infinity, this is really same as, we write it symbolically, right? V over V infinity. From this, we need to calculate the CP, so on all the points on the airfoil, you'll have V over V infinity or UE over V inf, from which you can calculate CP. And from CP distribution, you can get CX, CY, and then from that we can get CL, CD, and CMC over 4. So we'll be talking some more about how to get these things in this class and next class, but basically this is what you will be working on. So these two are the normal and axial force coefficients. These are lift and drag coefficients, and this is pitching moment coefficient, about the quarter chord. Okay, then there are the viscous flow data sets. So some of the data sets will be for inviscid flow, which means viscosity is not there. And almost everything else will be viscous data flow sets, and part B is entirely that, I believe. So these viscous flow data sets will include a CF distribution. So what is the CF? CF, in some books it's written as small c, small f. In some other books it's written as capital C, small f. This is the local skin friction distribution. Or local skin friction coefficient. And so this local skin friction coefficient is the skin friction force on a panel. So let me call that elemental friction force on a panel. Divided by half rho V infinity squared times area of the panel. So let's think through what that means. So if we take an airfoil and let's take a panel, for convenience I'm just going to call this 1 and 2 like this. When you actually derive your expressions, make sure you keep the ordering the way it is in the data files. So you will have CF1 and CF2 for these two panel endpoints, right? This is the panel, this is the endpoints, and each endpoint will have data. It will have CP, it will have CF. So let's call this CF1, CF2, and there is a scrubbing force or the friction force that's acting tangential to the panel, and that is, let's call that DFS. I'm just giving a name. It's not some kind of standard convention. What I mean by DFS is the frictional, or to put it in a different language, scrubbing force on the panel. So this, by definition, it acts tangential to the panel. So if you have two CF values, you just take a mean. CF mean for this panel is 1/2 of CF1 plus CF2. So this DFS is CF mean times half rho V squared V infinity squared times area of panel. And what is that area of the panel? So let's call this ds. This distance is ds. So CF mean times half rho V infinity squared times area of the panel is ds. ds is the length. Yeah, so some span-wise distance, let's call that dz, which is, you can always consider that to be equal to 1. So this is dF. Another way to talk about frictional force is to use the shear stress, tau. Tau is the shear stress, and this is frictional force per unit area. And tau is defined as is dFs divided by area of panel. So tau is simply CF mean. For this panel, the tau is CF mean times half rho V infinity squared. This is the tau at the wall. So this is shear stress at the wall. You can also have shear stress within the fluid, especially inside boundary layers and so on. But here we are talking about at the surface. Okay. Any discussion, questions? Are you all familiar with the tau at the wall? I mean, you've heard about it in other circumstances, right? Boundary layer theory or CFD or something. Wall shear stress is a big, important thing, important kind of aerodynamic property that determines drag and how boundary layers grow. So the reason you get shear stress at the wall is because of viscous effects. Normally you have a boundary layer, and as you look in the direction normal to the surface at this point or at any point, the velocity is zero at the surface because of no slip condition. So the friction brings the velocity to zero relative to the wall at that wall point. But as you go in the normal direction, the velocity quickly increases, and at some point, which is the edge of the boundary layer, the velocity becomes equal to the outer velocity in that region. So this, even though this boundary layer is very thin, the velocity gradient in the normal direction causes shear stress, and that's why there is shear stress here. So if you take a little fluid particle like this, there will be force acting this way on the top and this way in the bottom, causing shear. Okay. One of the big outstanding problems in aerodynamics, experimental aerodynamics, is to find a way to measure the shear stress in a reliable way, not in a lab setting, but out in the field, in an airplane wing, for example. If we could measure shear stress all along the airplane wing as it's flying, you'd get so much more insight, but that's been such a huge engineering problem. People have done it in the lab. Even in the lab, it's still a very messy thing to measure. Okay, so I'll go ahead and mention this, but you can use this reference, but you may also get confused too much if you follow it in too much detail. So potentially useful reference. is Anderson's book called Fundamentals of Aerodynamics, which I've listed in the syllabus. This is the book that's used in the undergraduate Aerodynamics 1 course. So this book gives expressions for integrating CP and CF distributions to obtain lift coefficient, drag coefficient, and pitching moment coefficients. But there is a big but here. You have to be cautious because Anderson derives these expressions for a different coordinate ordering. So in Anderson's book, the equations are derived for airfoils that are usually in the NACA format, which is you have a list of coordinates for the upper surface from leading edge to trailing edge, another list for upper surface, for lower surface from leading edge to trailing edge. So many of the expressions, at a minimum, the signs will be wrong. So there may be pluses that have to be minuses and so on. So I think you can use that as a guide. Go look at it if you want and see how it's done. But then you should probably put the book away and derive it on your own for this exercise. Okay. Questions? I think once you start working on it, you'll have some questions. So what we're going to do next is something similar, but expressions that help us to visually interpret CP distribution. So one of the things we'll do in this course is look at a lot of CP distributions. And I call it being able to read a CP distribution. The CP distribution is such an important thing in airfoil aerodynamics that it tells you a lot of stuff if you know and if you train yourself to try to understand what the distribution is telling you. So let's do that. And this is somewhat similar to what we have done, but still it's a little different. So although we are going to derive these expressions, I want to really make a note. These expressions are not going to be applicable for homework 1. So we are doing this for a different purpose. Don't go and plug these expressions into your code and say it doesn't work. It probably won't, because this is done for a different reason. And I think you'll see that when we get to the end of this topic. So in these derivations, so we are going to assume that the x coordinates on the upper and lower surface match up. And you'll see the reason why we are doing this shortly. So in other words, if you have an airfoil, we're going to say the panel on the upper surface, the endpoints will coincide, the x locations for the endpoints will coincide with those on the lower surface. And why we are doing that is because we want to integrate the pressures, just even visually. So we are trying to draw connections So because of this, if you have the x locations the same, then you can say if I take this panel and this panel, the resultant vertical, so this is the same x locations, and this dx is the x width of this panel. So the vertical force will just be delta y, which will be the vertical force on this portion of the airfoil. So if you take this and zoom in and just take this out for more detailed examination, so you have this panel here and maybe this panel here, right? So this is that portion of the airfoil, and we have some mean pressure which we will call PMU, and we'll draw it in the positive sense. Even though the actual pressure on the upper surface may be a suction, when you derive equations, it's always helpful to draw things in the positive sense, and then they'll turn out to be negative later on for some situations, right? So let's call this PMU. And on the lower surface, some other mean pressure. Again, we'll draw it in the positive sense, and this becomes PML. So PM is the mean pressure. Okay. So we'll convert these to CP. So CPU equals CP on the upper surface panel and CPL CPL is the CP on the lower surface panels. And these are mean values. So essentially I'm taking this PMU and PML and I want to convert that to CPU and CPL. So I'm going to give you folks a little exercise just to sort of get used to all these things. And so what I want you to do is write expressions, and do this now. Write, or you can derive it, whatever. Derive expressions for PMU and PML in terms of each one CPU and CPL respectively. So you'll have expression for PMU in terms of CPU and PML in terms of CPL and other quantities like V infinity. Okay, so just let's start with PMU. Just do PMU to start with. Get an expression for PMU in terms of CPU using all the things we have been doing in the past couple of 2 or 3 classes. Okay, I'm going to start a timer so we don't take too much time over this. Give 2 minutes starting now. Okay. What do you all have? So we want PM in terms of CP. Maybe we can start with the definition of CP. Is that helpful? Yeah, so, or if you have the answer, just give it to me. So some of you probably have the answer. PMU is, anybody? P in, okay, does this make sense or any disagreements? Right, so this is straightforward, and the reason is because we define Cp at any point as pressure at that point minus P infinity over half rho V infinity squared. Likewise, PML is P infinity plus CPL half rho V infinity squared. So if we go back and think about this picture, what is this delta Y, the vertical force on this portion of the airfoil in terms of pressures? Difference between the pressures will give, it won't give force, times the area, right? So it's difference between the pressures times the area. What area will we use? Will we use this panel area, this panel area? They're all oriented in different ways, right? Yeah, just the dx. So what is delta y is what we are talking about. So what is this delta y force on this portion of the airfoil? So delta y is, it turns out, is PML minus PMU, because PML is pushing upward generally and PMU is pushing downward, times the projected area is the projected area in the x along the x-axis. So that will be dx times dz, and that dz can be 1 or not. I mean, it'll fall out of the picture very soon. And the reason it is only dx, the dy doesn't matter, is because the dy portion will contribute to a horizontal force, which we are not bothered about right now. We are only asking about vertical force. So vertical force will be dependent on the x area, right? The x parallel to x area, so dx. And so this is the delta y. Now let's write it in coefficient form. And so that is half rho V infinity squared. So when you put the PML, PMU equations from here, the P infinities will cancel. So half rho V infinity squared CPL minus CPU times dx dz. And it's like the P infinities will cancel because uniform pressure, for example, on a closed body will not contribute to any force. Like if you have an airfoil sitting around in this room and it's not moving, there's atmospheric pressure acting, equal pressure acting all around, so it won't contribute to force. Like that, the P infinity will just fall out of the picture. So now we can say this is on the element. The total Y force is the total Y component of the force on the entire airfoil that will be integral 0 to c delta y, and that is half rho V infinity squared dz integral 0 to c CPL minus CPU dx. right? dz is the spanwise width, which will make sense to have it the same for all the panels, so you can take it out of the integral. And so you get this, CPL and CPU will vary along the chord, and so that's what you get. So let's convert this to coefficient form. So let's call this as C small y is the y force coefficient on the airfoil. And that will be the y force divided by half rho v infinity squared chord times dz. So that's the planform area of this little 2D airfoil. So now you see dz is going to drop out, and cy just becomes 1 over chord integral 0 to c cpl minus cpu dx. Okay, so dz has dropped out. If you take chord as 1, which is what we do in most airfoil plots, so if chord equals 1, then cy is simply integral 0 to 1 cpl minus cpu dx. So what does this, how does this connect to lift and drag? So this actually turns out cy is very similar to lift coefficient, because we're going to see that for small angles and typical flight conditions, this is practically the same as lift coefficient. So let's see why. We'll draw an airfoil and some typical lift and drag forces. Okay, so I'm going to draw V infinity at some angle, and I'll draw a resultant force like this. So this is resultant force R, and I'll draw lift and drag as the components perpendicular and parallel to V infinity. Like, that's how they are defined, right? So this is lift, this is drag. And this is all per unit span. Okay, but you can also decompose this as x and y. And so you get, this is y. Maybe I should have drawn it in blue. Yeah. This is L. Oh, sorry, this is y, and this is x. X turns out to be in the forward direction. So whenever I draw these things, alpha is pretty exaggerated. And the reason is to show things clearly, I have to draw a big angle. Usually it'll be between like 0 to 15 or something. What I've drawn is probably like 35. So you can transform L and D pair to X and Y pair, right? So the conversion is L equals y times cosine theta minus x times sine, y times cosine alpha minus x sine alpha. D is y sine alpha plus x cosine alpha. You will need this in your program too, because you're going to be calculating x and y, and then from that you'll get lift and drag. So alpha is small. So what do I mean by that? By now you have been hearing about small angle approximations in all kinds of places. Is 10 degrees small? 10 seems like a big number, right? 10 is not small. 15, 12. But we are saying most of the time alpha is small in normal flight conditions. Normal flight condition can be 10 degrees, 15 degrees. Why is that small? It's small in radians. So as long as alpha is less than alpha stall, for example, which is like maybe 15 degrees, all of this is actually going to be valid. So if alpha is small, cosine alpha is approximately 1 and sine alpha is approximately alpha. The sine alpha being equal to alpha is the small angle approximation and cosine alpha 1. But this works only if alpha is in radians. It took me a long time to realize this. Maybe sometime in grad school I finally realized, oh, this is what they mean. And I'm wondering if many of you are like that. You just kind of go on saying small angle all during undergrad, and then sometime later you think about it. For example, 10 degrees, right? Sine of 10 degrees is nowhere like 10. But if you convert 10 degrees to radians, it will be very close to the angle in radians. Even in fact 30. You can go to 30 degrees. 30 is what? 1/6. 30 is 1/6 of a radian, right? No. What is 30? Pi, it's pi over 6. Isn't it pi over 6? Pi over 6 is approximately half, right? 3.14 divided by 6 is approximately half. And sine of 30 degrees is half. So you can see sine alpha is approximately equal to alpha even for a high angle like 30 degrees. But you have to work in radians. Likewise, cosine alpha for 10 degrees, 15 degrees, cosine alpha will be very close to 1. So that's one reason if alpha is small. Additionally, if we have relative magnitudes of x and y such that x is much less than y, then what happens is you can take these equations, let's call these equations as 1 and 2. You can take, let's take equation 1 and we'll see that this so let's divide let's take this equation 1 and divide it by y on both sides. So L over y is cosine alpha minus x over y times sine alpha. And I've got all my page numbers muddled up. Give me a minute. Five, 8. Yeah, I think I'm okay. Okay, so what happens here is this is approximately 1 of the order of 1, right? It's actually very close to 1. X over y is a small quantity because we've already said that's our assumption. And sine alpha for small angles is approximately alpha, and it is small. So now you have product of two small quantities. And this term is much smaller than 1. So for example, even if you say x is 1/10 of y, so this will be 0.1. And let's say even this is 0.1. 0.1 times 0.1 is 0.01, right? So then this becomes about 1% of this. And you can say, well, that's small enough, I'm going to throw it out for convenience purposes. So what we get now is L over y is approximately 1, which means lift is approximately equal to y. And this is true for most normal flight conditions. You can actually call lift coefficient as approximately equal to the vertical force or normal force coefficient Cy. And now let's talk about equation 2. So equation 2 is d equals y sine alpha plus x cosine alpha. So let's do d over y is sine alpha plus x over y cosine alpha. And that's approximately equal to alpha plus x over y times cosine alpha, which is approximately 1. So what this gives is d is approximately y times alpha plus x. So the problem here is you cannot throw out anything because x over y is a small quantity, but it's only product of two small quantities that you can throw out if the other term is big, it's like the order of 1. So here you can't throw out anything because alpha is small and x over y is small, but you're multiplying it with 1, so you can't throw that out. So these are two small quantities that are added up, and it's not like one is huge and the other one is small. So you have to keep everything. And so d is approximately equal to y alpha plus x. So earlier you could say lift is approximately equal to y, but you cannot say that for d and x. You can't say d is approximately equal to x. D is not in fact d can be the opposite sign compared to x, and then we actually can show this even with this diagram. Okay, so if you go back to this diagram, you can see in this situation x is negative because it points this way, but d is always positive, d is this way. So even though L and y are of, you can replace y with L, you cannot replace x with d. They might be like d might be plus 0.01, x might be minus 0.03. You can't say they're the same. So anyway, so this is a little bit of a detour to say how these things vary, but the main point I'm coming to is CL is approximately equal to Cy, and we wrote Cy earlier as 0 to 1 CPL minus CPU dx. What does this graphically represent in a CP distribution plot? So if I draw a CP distribution plot, like this is x over c, this is 1, this is 0, so this is a CP distribution plot. Remember, we plot CP as upside down, so this is plus 1, this is 0, minus 1, minus 2, minus 3, something like that, and this is the upper surface curve, and this is the lower surface curve. What is this integral? Go ahead. So it's the area under which curve? This curve or this curve? Inside the curves, right? The area between the curves. So this area is really what this integral represents. So CL equals area inside the CP versus x over c plot for some angle of attack. And that's what this also tells us. This expression is the same as what is shown graphically. And for any given airfoil location, like let's say this little portion of the airfoil, the lift over this portion of the airfoil is actually equal to the area between the two curves for this portion of that airfoil. Okay, so we'll stop here and I'll resume from here in the next class. Remember, there's a pop quiz.